All right. Hi, guys. I'll introduce myself again. So I'm Chong Tang. Currently, I'm second year PhD student. My supervisors, Dr. Kevin Chetty and Professor Simon Julia. So I'm very happy to introduce my PhD project, which is about using deep learning strategies to improve the passive Wi-Fi radar sensing system. So today's seminar, I will cover these topics. So I will briefly introduce my PhD project, and also I will quickly go through the some results I've already done, and I will talk about what my future direction is. So firstly, the motivation of my project is because currently in the passive Wi-Fi radar sensing system, there is some issues like the result is highly affected by the multi-path filters, and also it's sometimes it's very complicated to extract high quality features, and also we can't always get a very high classification accuracies, and also it's a very practical issues. The data collection is really hard to do, so we can't easily get a large number of the data. So based on these facts, I'm going to use the deep learning strategies to improve and further develop the passive Wi-Fi radar sensing system, and which include some aspects like signal processing, feature extraction, or classification, and many other applications. So basically, the first thing is what is passive Wi-Fi radar system? So basically, it's based on it's a kind of the passive radar, which is a form of the bistatic radar system, has a surveillance channel and reference channel, and we use existing Wi-Fi communications to passively detect the target's motion and use cross-correlation signal processing method to extract the Micro-Doppler signatures. This is the passive Wi-Fi system. This is the general layout of our experimental experimental layout. So basically, we have two antennas here. One to directly get the signal source signals from the Wi-Fi AP, and another one gets the reflected echoes from the targets we monitored, and also two channels we are connected with the USRP, which is for real-time data acquisition, and also for the synchronization the two antennas. And finally, the signal processing will be done in the lab view. Here is a general signal processing framework of our systems. After we get raw data, we use the cross-ambiguity function to process that, to extract the Doppler signatures, and using some method for the denoising, and finally get the spectrograms or just the cut results. And the final stage will be the application stage. We'll use some classifier to do the classification or many other applications. Okay, so another question is why I want to use deep learning. Why I think deep learning is good for the passive Wi-Fi radar systems. I made some comparison between the deep learning methods and the current methods, I call that traditional methods. So in the passive Wi-Fi radar sensing system. So firstly, the deep learning method is kind of data-driven algorithms. That means it is able to extract features or learn some feature extraction methods from experimental data. So this is very good things because for the model-driven algorithms, it's just designed for some specific situations. But in the real life, there is some scenarios we can't handle that with just a single model. So for the deep learning, we can automatically learn the different features or different models from the experimental data. So I think it can handle various cases in the real life experiments. And also, the deep learning methods can be separately used at any stage without modifying the current framework, which I mean is, for example, after we get raw data, we can just insert some deep learning methods here, like using complex value neural network to process them, or after we get path, or before denoising or after denoising any stage, we can directly use the deep learning strategies to do that. But for the other algorithms, sometimes it's not very convenient to modify them because we need to do a lot of recoding. Sometimes we need to totally change the current signal processing framework. That's why the deep learning is, I think, it's in this term, in terms of this aspect, is better. And also, the deep learning can do a lot of things which what other algorithms can't do. For example, for the classification results, currently the best result can so the best classifier most of the best classifier is based on the deep learning algorithms. So so in this case, only deep learning methods can give us the very good results. So in my project, I used the following techniques or the systems. So first of all, is a passive Wi-Fi radar system, which developed by the Dr. Wenda Lee and Dr. Kevin Chetty and our research groups, and also the C-Humulator, which is a wireless sensing simulation tool developed by Dr. Shelly Vishwakarma, also in our group. And also, I also use the mocap system for like sometimes for ground truth data or sometimes for C-Humulator. And I use the phase-based system, which is a mark-based system, and also Kinect system, which is like using deep camera, which is a markless-based system. And I also applied various deep learning algorithms, including CNNs and like recurrent neural networks like long short-term memory, and also some generative neural networks like GANs or the autoencoders, something like that. Okay, with these methods, I have already developed achieved some progresses. So I will mainly focus on the idea how I designed the framework, and I will quickly go through some results later. Yeah. So the very first one is Micro-Doppler spectrogram denoising. So the reason why I developed this framework is because I found that the current result from passive Wi-Fi radar, there is still some noise in the Micro-Doppler spectrograms. For example, the Micro-Doppler spectrogram will be affected by the environmental clutters or the multi-pass clutters. So even we apply some like traditional denoising methods like plain algorithm to remove the DSI signals, we still can see some residual noise. So the fact is, the higher quality of the Micro-Doppler spectrograms will get higher classification results. So that's why I think we need a better denoising method to process the Micro-Doppler spectrogram. And also, there is already has some deep learning based denoising methods which use artificial noise like AWJ noise to create noise training pairs. They use the AWJ noise to create some noise which they think that is close to the real noise. But I think this model is not good enough because it's just AWJ noise, you know. So the aim of this study is trying to learn from the measured noise, which is a real noise, to create a robust measurement noise modeling methods instead of just using AWJ noise model and to denoise the Micro-Doppler spectrum. So here is the framework. So firstly, we have the two systems. One is passive Wi-Fi radar system. We will get measured spectrum from PWR system. And after we get a long recording, we will extract noise, real noise from this recording, from these regions. These regions don't have any activity signals. So we can think this region only contains some environmental clusters, which we don't want them. We want to denoise them. And after we get these things, we can see this is the samples from the real noise. And we use the GAN network. The GAN network has two like small models, small networks, which is generator and discriminator. We use this real noise as the real noise sample or just the real sample. And we use the generator create a fake sample from some random noise, some random vectors. Yeah. And after we get these fake samples and also these real samples, we use the discriminator to make these fake samples get closer to these real samples. Finally, we can only use this generator to generate some close to nature noise patches. After that, we use the mocap data and pass that into this accumulator, get some plain simulated spectrograms, and add them together to create the noisy simulated spectrogram. So we will use this noisy simulated spectrogram and also the noise patch as the features and as labels respectively, and train a denoising convolutional neural network to get the final denoiser model. Firstly, I will show how the new noise look like. So here is a clean simulation, and here is a measurement. See, we can see the difference between the clean simulation and measurement data, right? And after I add the noise patch, you can see the after the noisy simulation spectrogram looks like closer to the measurement spectrograms. This is how the new noise looks like. And also I show some denoising results here. Here, the left columns are the measurements data. You can see there is some environmental clusters or some clusters here. We can see that. So these features will affect the classifier to get high classification results. So after we apply the denoising network, you can see we remove these things. Even we apply the same denoiser on the different data set. For example, this is activity recognition data set. We train the denoiser on this data set, and we test it on the hand gesture data set. We can still see a very good results. And we also quantitatively analyze the different modeling, the noise modeling methods, like mixed one, which is a 50% AWGN plus 50% uniform distributed noise, and AWGN, and our modeling methods. And we also apply the different neural network structures to denoise that to see the results. You can see our noise modeling methods can always get the higher result, the best results. And also for in the classification results, we can also see we can always get highest classification accuracies with our measurement noise modeling methods. So yeah, this is basically the denoising, how we using the deep learning methods for denoising the Micro-Doppler spectrogram. And this is the second one. This is my latest research actually, so which is the latent feature mapping based Micro-Doppler spectrum enhancement study. So for this study, actually I want to after I get the denoising results, I realized one fact that there is still isn't an effective way to handle the multipath clusters. So if you remember the previous framework, we only extract the clusters, those noise from the region which no activity happens. But multipath clusters always mixed with motion information. So the challenge here is it's very challenging to separate the motion information and or multipath clusters from the mixed signals. So I'm thinking, can we separate motion information and various clusters in other space, similar to kernel trick in SVM? So in SVM, if we can't separate the data from the lower space, we can use kernel trick to transform that to a higher space or lower dimensional space and try to find a plane to separate that. So that is so I think we can apply the similar idea in this Micro-Doppler spectrum enhancement or denoising studies. So I designed this framework. So it's basically based on a variational autoencoder, so which is this line. So we have an encoder and we have a decoder. So and also the change here is I attached a adversarial structure after the encoder extracts some like latent features, and I used this adversarial structure to map the measured features to the simulated features. Because simulated features, simulated spectrograms and measured spectrograms for the same activities, they actually contains the same motion information. So, but just because the measured spectrograms contains some noise, so the feature here and here has some difference. But if we can use a versatile structure to map these different features to the simulated features, so that means we can directly remove those noise, and we can directly get the clean motion information. This is the basic idea. So I designed a three-phase training schemes. In the first scheme, I put the simulation data into the autoencoder and train the encoder and decoder according to the reconstruction laws. So this stage will make the decoder has ability to generate some simulation-like output according to the latent features. And the phase 2 is used for the feature mapping. So we firstly, from phase 1, get some simulated features, and then we feed the measured data into the encoder, and we will get some measured features. And then we use adversarial loss to map this fake, so which is actually the measured features, to the real features, which is the only content motion information's features. So we map this fake one to this real one, so that for the same activities, the encoder can extract the same features for both measured spectrograms and simulated spectrogram. Okay, then after we finish this, we move to the phase 3. So the phase 3 is used to double check whether the output enhanced data contains the same content as the original measured input. So we use the KL divergency. We feed that back to the encoder and get the latent features for this enhanced data. And we using KL divergences to measure the difference between them and try to minimize this difference. Okay, we do the experiments in two scenarios. One is line of sight, so the people inside this room and directly get some data. And the second one is through the wall experiment. We train our FMNet in these LOS scenarios, and also can test this model on this through the wall scenario. Here is some basic results. This is for the LOS experiment results. The first row is for the measured data. The second is simulated data, and this is enhanced data. We only input the measured data into the FMNet and see here is just the output. We can see we can get a very clear pattern here, and it's very close to the simulated data. And here is through the wall experiment results. We also, the first row is for the measured data, and this is our FMNet results. And here we try using other training schemes, also the different networks to compare with our FMNet. We can see only FMNet can perform very well. So yeah, and based on the enhancement network, I actually proposed another novel classification idea. So here is a traditional classification idea. We train this classifier with a measured spectrogram, and then when the new samples goes in, we're using this classifier to classify the new samples. But after we train FMNet, we actually can do this in this way. So we train this classifier with simulated data, because the simulated data, theoretically, we can get unlimited number of the training set for the if we only use the simulated data. So that makes our classifier always get very high classification accuracies, and also classify the simulated data can provide us very clear motion patterns. So that will also improve the classification results. So instead of directly classify these measured new samples, we firstly use FMNet to enhance that, and then use this classifier to enhance to classify the enhanced spectrograms. So this is the new classification framework. So from the results, we can see only our trained simulated data test enhancement measurement case can always get the highest accuracy. And also, if for this train original measurement, test original measurement case, after we gradually increase the number of training samples, but after some stages, we don't have more measured data. So we can only stop here. The highest accuracy can only stop like 92%. But for the for this train simulated case, we can keep increase the number of the training samples. So we can see here, we can keep get higher classification accuracies. So this is advantages of our new proposed classification idea. Yeah. So the third one is the spectrum augmentation. So in the classification, actually, from the previous slide, we can see for the classification result, if we want to get the higher classification accuracy, we must make sure we have enough training data set. But in real life, it's very time consuming and very hard for radar sensing system to get a lot of data. So I and Shelly proposed like scheme using the simulated data to augment the like training data set. So the experiment setup is like that. We use the passive Wi-Fi radar and Kinect sensor simultaneously collect data and generated simulated data and measured data. We can see the similarity between them and also compare them with the ground truth. We can see how good they are. Yeah. So after we get this simulated data, we proposed two kinds of augmentation schemes. The firstly, we call that augmentation study. So we will use some fixed data as the test set, and we gradually add some simulation data into the original training data set. We can see this is after we augment the training data set. So the size of training data will keep increasing. So here is a result and some observation we can get from these results. We can say for the same S, the S means the percentage of simulated data augmented with the measured data. So for the same S, we can see the classification accuracies increases with an increase of M. So that means more measurement data can provide us higher classification results. But normally we can only get very limited measured data. So we can see here on the same app, after we augment the data set with our simulated data, we can still get a very good improvement. And for the smaller M, the more pronounced improvement we can see here. Yeah. And this is the second scheme, which is the replacement study. So we actually fixed the number of training data. So in some case, we will get some bad samples in our measured data, or the like activity, like we have 6 activities, but some activities we only have very limited samples. That makes the whole data set unbalanced. So we can replace those parts with the simulated data. So with the overall the size of training set will be fixed, but some measured data will be replaced with simulated data. This is a second replacement study. We can see from the result that still for the same role, we can see with the M increased, with the more M we have, we can get higher results. But this time for the same column, we can see when more and more measured data replaced by the simulated data, the accuracy dropped. So this replacement study only works for some. So we need very care about. We need to be very careful to pick the number of simulated data used in this replacement study scheme. So yeah, still yeah. Okay, this is for the augmentation study. We summarized some very useful practical suggestions here, and also in our publications. The very good news is some other researchers have already cited our publications, and they use the same schemes in their studies. They can also see the improvement, which means our research works in many other cases. We also have some new development based on this augmentation study. So if you remember the denoising framework, we can have the measurement noise modeling methods from this denoising framework, and we create some noise patches, and we add these noise patches on the simulated data, so that we introduce some environmental factors into the clean simulated data, make them close to the measurement spectrograms, and then we we use this noisy simulated spectrum to augment the training set. We can get the better results. So our progress, if you are interested in that, we have some publications about that. Okay, and the last one is kind of the application using deep learning to in some passive Wi-Fi radar application scenarios. For example, for the people counting and occupancy detection. So for the people counting and occupancy detection, it's very hard to extract features because with the number of the people increase, you can observe that the spectrum becomes more and more complicated. So we want to investigate whether the CNN can effectively extract the useful features in this case. So we design experiments like we have 4 peoples, but the latest data set is 6 peoples. We can still get very good results. But the previous data set, we have 4 peoples, and we enter this one room one by one, and then left this room one by one, and we got some data, and we can see if we visualize the spectrum, we can see this is an empty room. Although we can see something here, but the amplitude of these Doppler beams is very low. And for the one person, you can see clear the motion pattern of this one person. But for the two people, from the 2 people, the spectrum become more and more complicated. We can't directly extract features from these spectrums. So we applied the different CNNs to try to classify them and extract the features. We can see the CNN can effectively attract the features and get the very good classification results for all of them. We can see that among them, the FMNet, which is has a deeper neural network structures, can get the better results. Yeah, and also we tried a different window size. Here, window size means the length, the frames we used to train here. So like for the 10, we used the 10 here this spectrum to as a one sample to train the classifier. So yeah, we can see that with the window size increases, we can get the better results. Yeah, so basically from the progress I introduced before, previous progresses I introduced, we can see how good the deep learning can help the passive Wi-Fi radar achieve the better results in terms of getting the better high quality Micro-Doppler spectrum or extract features, get a higher classification results, etc. So at the current stage of the project, so our results looks very good and outperformed many other traditional algorithms, and also compared with other existing deep learning based methods, our new like framework looks better. And also for the future, if we can further optimize these neural networks, I think we can get the better results. Yeah, and for the future's work, apart from the keep developing the previous framework, the very cool things I want to do is I want to reconstruct human skeletal model only from the Micro-Doppler spectrum. So here is the framework. So I just proposed this framework. I haven't tried, but I think it should be works because according to my experience from the previous progresses. So firstly, we will get some mocap data and skeleton models, and we use simulator to generate some simulated results. And also we have passive radar to get the measured spectrum. If we can design a neural network here to extract the features and find the similarity between them, we will get final model because this simulated data is directly related to the skeletal models. So, but after we get the enhancement framework works, I already have an idea how to do that. We already built the bridge between the measurement spectrum and the simulation spectrum with the enhancement framework. So there, the bridge has been built. So the next step is the only things we need to investigate is how we can find the relationship between the simulation and mocap, or how we can directly find the relationship between the measurement through this bridge to this mocap data. So this will be the next stage I'm going to do. So hopefully I can achieve that in the rest of my PhD project. Yeah, and I think that's all. I just quickly go through all the things about my PhD project. Thank you so much. And if you have any questions, I can discuss that with you guys. Thank you.